In this video, we're going to look at the definition and some simple Laplace transforms. I'm going to define what a Laplace transform is, and we're going to compute some simple ones. The method of Laplace transform gives us a way to solve linear differential equations. It works for linear constant coefficient equations of any order and can also be applied to systems of linear differential equations. The important thing that we get out of this is it converts a problem in differential equations just into a problem of algebra. So here's a definition. If f of t is called a piecewise continuous on the interval from 0 to infinity, if it is continuous, and I don't know why there's a hyphen in there, just ignore it, except possibly at a finite number of points of t sub k on any finite subinterval of 0 to infinity, 0 being inclusive, and at each t sub k, both of the limits exist. So as t approaches this point sub k from the left and from the right, they both exist. This means the function cannot go to negative or infinity or positive infinity on either side, and if it does, then it's a point of discontinuity. So as an example, this is piecewise continuous. So the fact that it has a corner here is not a big deal. It is piecewise continuous on the interval from 0 to infinity, because even down here, this curved piece, this limit exists on the left side of 4, and it also exists on the right side of 4. So this is a piecewise continuous. Now this example is not piecewise continuous, that even though we have a limit that exists on the left side of 2, it doesn't exist on the right side of 2 as a numeric value. We're not talking about when Calc 1, where we talk about, well, it does exist as infinity. No, that is behavior of the graph. And we're looking for this to actually approach a point. A function is said to be exponential order if there exists some constants m, a, and t such that the absolute value of f of t is less than some m e raised to the at for all this lowercase t greater than the uppercase t. If f of t is a piecewise continuous function of exponential order, the Laplace transform of f of t can be defined as this. The Laplace transform of f of t from 0 to infinity of e raised to the negative st f of t is equivalently equal to the antiderivative of s. Let's start when f of t is 1. When f of t is 1, then I'm doing the Laplace transform on 1, which gives me e raised to the negative st dt, which can also be done as the limit as b goes to infinity, because this is an improper integration. Because it's an improper integration, we're going to take the limit. And when that happens, we have the limit as b approaches infinity of this. Putting in b and 0, I have e raised to the negative bs over negative s. Well, as b gets really large, because this is e raised to the negative exponent, it's going to go in the denominator, which is going to dominate, so this is going to go to 0. So if that goes to 0, the only thing left standing is e to the 0, which is 1, over negative s. Those negatives cancel, so I get 1 over s. So the Laplace transform function for the function of a constant is equal to 1 over s. Do the same thing for if f of t was an exponential. This is the Laplace transform. Let's look at what happens when we have sine and cosine. Well, if I have e raised to the b t sub I, where I is a complex number, then I'm going to end up with these individually. See how the I right here? Check that out. And this is what we end up with. So we end up with 1 over s minus bi. Using complex conjugates for the Laplace transform of cosine, the Laplace transform of sine of b of t is s over s squared plus b squared, and b over s squared plus b squared. The Laplace transform is a linear operator. That is, if I have the Laplace of some a constant multiplied by the function f of t, some b constant multiplied by some function g of t, I can just factor that constant out and do the Laplace of each one of those individually and then multiply by that constant. All right. You're like, what? Well, let's go through a couple of examples. I want to find the Laplace transform of 6e raised to the negative 5t, e raised to the 3t, 5t to the third minus 9. Well, using the formulas that we have up above for e, and the fact that I can just pull the 6 or the 5 or the whatever it is constant out 9, then I can write this as 6 multiplied by 1 over s minus the negative 5. I'm going to make my s's, see how my 5 and s's go the same? I'm going to make that a cursive. Plus 1 over s minus 3. That takes care of this one. Now, I've got this 5t to the third. I haven't talked about that. So let's talk about when I have t to the n. The Laplace transform when I have t to the n will be n factorial over s raised to the n plus 1. So I guess I should have gave you that one too. So then 5 is just a multiplier. My exponent is 3, so it's going to be 3 factorial over s to the 3 plus 1. And then minus that 9 multiplied by the constant 1 Laplace, which is 1 over s. So what I basically have is 6 over s plus 5 plus 1 over s minus 3 plus, well, I have 3 factorial is 6 times 5, which is 30, s to the 4, minus 9 over s. And that's my Laplace transform. This video, we're not going to do much with them right now. We're just going to figure out what Laplace transforms would be. Oh, and we should say this is f of t. F of s, cap f, the antiderivative. G, cap g of t. Well, we know this is the cosine of 4t. So this is going to be 4 as a multiplier. Cosine was s over s squared plus that 4 squared, minus 9 multiplied by my 4, which is coming from right here, over s squared plus 4 squared, plus 2 multiplied by s, 2 is coming from here, s squared plus 10 squared. So then this just becomes 4s over s squared plus 16 minus 36 over s squared plus 16. Oh, I could combine those. Probably won't, though. Plus 2s over s squared plus 100. Now let's take a look at my last example here. So g, capital G of t, is equal to, I don't know why I keep wanting to do g of t. It's g of s. Is that what I did up there? G of s? Oh, it should be g of s too. Because I took something in a function of t, and I turned it into a function of s, so a function of s. First one's pretty straightforward. It's just 1 over s minus 3. Second one is a cosine, so we know that is going to be s over s squared plus 6 squared. Oh, what do we do with this? We have e to the 3t cosine of 6t. Well, there's another formula for that. All the formulas that you're going to use in this class are at the bottom of your notes, and we'll get there in a minute. So I have e to the t, e to the 3t cosine 6t. This, generically, if I have e raised to the at, the cosine of a bt, then this, again, this is all at the end of the notes. It's going to be s minus a as a Laplace. It's not equal to, the Laplace transform would be s minus a the quantity squared, plus b squared. So using that, my last term is going to be s minus 3, because my a is 3, over s minus 3, the quantity squared, plus 6, the quantity squared. I can clean this up just a little bit. It's not much of a cleanup. This is going to be 1 over s minus 3 plus s over s squared plus 36 minus s minus 3, the quantity squared plus 36. Now, disinclined to multiply stuff through in the denominator and combine it, I'm probably going to leave it just like that. Because you know me, I'm not a fan of multiplying stuff in the denominator, so I hope that it kind of shakes out, but sometimes it doesn't. Okay, so now we're going to transform the derivative of f of t. We're going to use integration by parts from calculus 2 because that stuff never goes away. And so I have the Laplace transform of f prime of t. Goes all the way through. And we get down to here. So f prime of t is going to be the s times the Laplace transform of f of t minus f of 0. And for the second derivative, I'm going to get the s squared, the Laplace transform of f of t, plus s times f of 0 times f prime evaluated at 0. So if I'm asked to find the Laplace transform of g of t is equal to t raised to the 3 over 2, then the first thing I'm going to do is see if I've got some formula that's going to work for me. Again, look at the notes at the end of this section. And I know that the square root of t is going to give me the Laplace transform of the square root of pi over 2s raised to the 3 over 2. But we also have another one. We have, if I have t on my list, t raised to the n minus 1/2, well, t raised to the 3 over 2 must be equal to, using this, t raised to the, so that would be 3 over 2 is 1/2, so it would be 2 minus 1/2. So I would use n is equal to 1/2. I have another formula in my table at the end of these notes. I have this t to the n minus 1/2 is going to be equal to 2n minus 1 raised to the square root of pi multiplied by the square root of pi, 2 to the n, s to the n plus 1/2. Well, my n to get 3/2 must have been 2. So, not equal to, but that's what your Laplace is. So your g of s is going to be equal to, well, 2 multiplied by 2 minus 1 multiplied by pi divided by 2 raised to the 2, s raised to the 2 plus 1/2. So this is just going to be 3 the square root of pi over 4 s raised to the 5/2. Okay, let's take a look at your next example, which obviously seems to be missing. But what should have been here was the Laplace transform is equal to the integration from 0 to infinity of e raised to the negative st of t dt. Now, we know from integration by parts from up above, this can be evaluated then as, well, let's start with our u's and v's. U, a good choice for u would be t. That means du is equal to dt. And dv is equal to e raised to the negative st dt. That means v is equal to e raised to the negative st. So then this integration becomes t e raised to the negative st divided by negative s, evaluated from 0 to infinity, minus e raised to the negative st, the integration of from 0 to infinity, divided by negative s dt, and then I should have a negative s right there, which is equal to, well, as I let t go to infinity, I'm going to have t divided by e raised to the negative st. So that's going to go to 0. And I'm going to put in 0 for t. And I'm going to get minus 0, so still 0. So then plus, by bringing out this s, and this negative becomes a plus, 1 over s, evaluated from 0 to infinity, of e raised to the negative st dt, which we know is going to be 1 over s, e raised to the negative st divided by a negative s, evaluated from 0 to infinity, which is then going to give me 0 minus becomes plus 1 over s, multiplied by an additional 1 over s, so I get 1 over s squared. And I'm going to let you do C. Similar to what I did, integration by parts, do the evaluation. We'll do it in class if you'd like. This is the table of Laplace transform, which I will give to you for each one of the tests moving forward. So if you can find the Laplace transform here, then use it. You may have to do a little bit of combinations. We'll go over those in class. We won't go through all of these in class because it's beyond the scope of this class, but it is, here's the table that I'm going to give to you, and we'll go through any of this you'd like to in class. And that's it for this section. Nice, easy peasy. Let's start out finding Laplace transforms.